Hi everyone, and thanks for giving me the opportunity to present this exciting and ongoing project where we use gravitational lensing on the poorly explored milli-arc-second scale to detect supermassive compact objects, like for example primordial black holes or dark matter halos on subgalactic scales. It is now known that ordinary atoms make up the 4% of the energy content of the universe, and the remaining 96% is made of unknown forms of energy and matter. In the standard cosmological model, this matter is in the form of cold dark matter, and therefore the so-called lambdaCDM model. And this model is quite successful in many predictions, but it also has some weaknesses. And one of them is that it predicts a number of dark matter halos on subgalactic scale, which is far above the observed number. So in this plot, you see in the gray area, you see the exactly these subgalactic scales. That is where we have let's say, less robust observational constraint. But as you can see, is also where different dark matter models make very different prediction on the expected number of dark matter halos in this range of masses. Therefore, a good estimate of the number of dark matter halos in these subgalactic scales may help in discerning the nature of dark matter. However, there is a complication, and is that dark matter subhalos with masses below some in 10 to the 8 solar masses are not expected to form galaxies. So the only way to detect them then is through their gravitational effect on ordinary matter. And therefore, gravitational lensing seems to be one of the most promising way to look for them. But are these dark matter subhalos dense enough to make strong lensing on sources in the background? Well, the dark matter mass distribution within dark matter halos follow a nearly universal density profile, the so-called Navarro-Frenkel White. And recently in 2020, Wong and collaborators studied in detail the halo concentration within simulated dark matter halos in function of their masses. And they found, as you can see here, that the dark matter subhalos are significantly more concentrated than galaxy cluster dark matter halos. So there is no reason why basically these, at least at the core of these dark matter subhalos, they shouldn't make strong lenses on background sources. And because of this, and because of the high density and small masses, we can consider them as compact objects. And we know that in gravitational lensing, compact objects are well approximated by point mass lenses. And we know that a strong lensing from point mass lenses produce two images of the same source, which are separated by whose separation is given by this formula here. That for order of magnitude estimates and for lenses and sources at cosmological distances, we get from this formula that for example, for a compact object, for a lens of a compact object of 10 to the 6 solar masses, we expected an angular separation between images of the order of 1 milli-arc-second. And more precisely, for supermassive compact objects, so with masses between 10 to the 6 and 10 to the 9 solar masses, we expected these images separated between 5 and 100 of milli-arc-second. That's why we call this system MIlli-Lenses. So then the most the most direct way, let's say, to explore these very small angular scales is through the high resolution of very long baseline interferometric data. Therefore, we use data publicly available from the AstroGeo VLBI FITS image database. which contain mostly VLBI data of active galactic nuclei, mostly coming from astrometry program. Therefore, there are mostly compact radio sources which are observed in multiple bands and at multiple epochs. And at the time we performed this search, we downloaded visibility data, multi-frequency and multi-epoch for almost 14,000 sources. And we perform a stacking of images in case for those sources where we have multi-epoch data. And then for the visual inspection, we follow the idea of the Citizen Science Project. We create this web page. You can see here an example. As an example, the screenshot, and we involved 5 PhD scientists and 9 undergraduate physics students from the University of Crete in the search for this MIlli-Lens candidate. And we asked them to mark as a gravitational lens candidate sources where multiple compact components in at least one band were present, as this example in the left, and possibly instead discard the sources where a classical core jet structure like the example on the right was present. After this first step, we selected 950 candidates. We also introduced a quality check for the search, introducing within the sample 200 mock lenses that we created simply creating a fake secondary compact component in any place within the field of view. And we inserted this then 200 mock lenses within the sample to be checked. Then we found that at the end of this first step, 8 of them were missing, but fortunately 6 of them were missed by 2 persons together. So we inspected then the sources checked by these 2 persons, and in this way we found 4 more lens candidates, and we were able to assess a final loss rate of 1%. Then we performed 2 more steps in this visual inspection that were performed this time by people in the collaboration that are expert in VLBI images of either AGN jets or gravitational lensing. And so the total number of candidates then at the end of this multiple step of visual inspection was 59. And then we finally perform a last step, excluding sources based on the surface brightness preservation criteria. In gravitational lensing, we expect the surface brightness of multiple images to be the same. Therefore, in this case, we use an apparent surface brightness ratio lower than 7, so not very stringent, to then finally select the 40 most probable candidate that here you have. So here I share with you the list of 40 MIlli-Lens candidates that we found. And I want, just as a summary, to remind you that all these sources have a multiple compact component on mass scales in at least one band, and an apparent surface brightness ratio between components lower than 7. Then, based on spectral index information, we also suggested 2 sources which have a higher probability of being MIlli-Lens candidates. And that means that they have similar flat spectral indices between the components. And then a third, as you can see here, a third source where we don't have any spectral index information. We hope also this result to be present, to appear soon in the archive. If none of these sources will be finally confirmed as a MIlli-Lens candidate, because of their morphology, they can still be investigated as compact symmetric object or supermassive binary black hole candidates. The first one are the young counterpart of extended radio galaxies. And the second one is self-explanatory. And let me say that in both cases, we are talking about poorly understood objects that deserve to be studied. So we checked in literature and we found that of the 40 MIlli-Lens candidates, only 4 were classified in literature as either CSO or GPS sources. So having multiple compact components, the remaining instead 36 sources are unclassified in literature. Then we proceeded to ask, and we obtained time with the European BBI network for the follow-up observation of these 40 MIlli-Lens candidates to observe them at 5 and 22 gigahertz for a total amount of 140 hours that were split in 5 sessions. Since the calibration and analysis of this data is still ongoing, I will just show you some preliminary result on a couple of sources. So this first source, J0527, is one of the 2 sources that we suggest as most probable MIlli-Lens candidate based on spectral index information. In our new EVN 5 gigahertz image, we confirm the double compact structure of the source. The component still pass the surface brightness criterion, but we were able to exclude the third component, which is instead visible in the image at 4.3 gigahertz in AstroGeo catalog as a most probable an artifact. So based on that, it looks like that the source still pass our initial selection criteria to be considered as a MIlli-Lens candidate. But when we, for example, compute the flux ratio between the component at the 2 closest frequency, that in gravitational lensing we expect to be preserved among epochs, we find instead some discrepancies. So at the end, most probably this source will be discarded as a MIlli-Lens candidate, but obviously we still want to wait for the result from the 22 gigahertz. Another source instead is this one, J0237. Here we think that what played a major role is the variability of these sources. We think that in the AstroGeo epoch, the source, most probably an ordinary quasar, was ejecting a new component from the core that is present as a secondary compact component, while in our new EVN instead epoch, it shows us an ordinary core jet structure. And this scenario, basically of a simple and ordinary quasar image, is supported also by the astrometric position of the optical emission as inferred from Gaia, which is close to the core. That is where we expect most of the bulk of the optical emission coming from in quasar, and not instead in between the 2 compact components, as we would expect in case of gravitational lensing. Now just let me briefly give you a brief overview of the future of this project, because what I presented to you so far was a pilot search for a bigger project where we plan to apply the same search, but on a more extended and complete sample of sources. Because the beauty of this project is that if it is performed on a complete sample of sources, even if we don't find any MIlli-Lens, we can still put a tight constraint on the abundance of a supermassive compact object in the mass, in the range of masses of interest. This was, for example, done in a pioneering study by Wilkinson et al. In 2001 that was following the approach by Press and Gunn 1973. They performed this search on a smaller sample, so 300 sources. They look for compact, multiple compact component on a scale between 1.5 and 50 milliarcsecond to constrain the mass density of supermassive compact object between 10 to the 6 and 10 to the 8 solar masses, and they found to be less than 1% the energy density of the universe. Since in our project we will use a sample that is an order of magnitude larger than the one in Wilkinson et al. 2001, we will constrain the abundance of supermassive compact object with masses, in this case, between 10 to the 6 and 10 to the 9 solar masses, with an order of magnitude better precision than in Wilkinson et al. 2001. And last things, if you have a look at this plot, if you compare the our constraint in case of null result with the prediction from the lambdaCDM model in case of dark matter halos only free floating in the field, you can see that our constraint will be well below the predicted number. This means that if the prediction is correct, we have to see them. This instead was not the case in the previous study of Wilkinson et al. 2001, where their constraint was still above the predicting number. And then here I leave, yes, I leave you my conclusion slide. Thanks for the attention.
Okay, thank you very much, Carolina, also for finishing before the allocated time. So we have time for several questions. So again, if you'd like to ask a question, please raise your hand or use the chat. Yes, Antoni, go ahead.
Yeah, my question is, it's not clear to me, where is the lens? Is it at the halo of the source? Is it a sub-halo in the halo of the source? Is it in our galaxy, or can it be anywhere in between?
Yes, thanks for the question. It's indeed a good question. Yes, so we are probing obviously a different scenario and different object here, because what we have, the constraint that we have in this case is only on the masses of this compact object that are making the lens. So they actually can be of different nature also, and therefore they can also have different location. So for example, we cannot exclude obviously that we can have MIlli-Lenses from, for example, supermassive black hole at the center of galaxies. Something in between, obviously in the foreground, so in between the background source and us. But we can also explore the different nature and location, for example, for these dark matter sub-halos that can be either closer to dark matter halo of a galaxy, so in the neighborhood of a bigger dark matter halos, or they can also be free floating in the field. So in this case, maybe we don't have any galaxy associated. And the same, it works also for example, primordial black holes.
But then, all right, so, but then it is important, the line sight is important, because if you go through a dense region of the the cosmic web, then you have a higher chance of finding such a free-floating massive object without a galaxy and so on, or even on the parent halo of the galaxy that emits, of the radio galaxy that emits the radiation. So does that change, like this this non-homogeneity of the universe, does that change your upper limit?
Here, obviously, we are we just perform a pilot search, so we are still trying to make this computation as much precise as possible. For this plot, I mean here. Here, for example, the lambdaCDM prediction, so the black line that you see here, it gives you the number only of dark matter halos for a different range of masses, only free floating in the field, for example. So it's so this is already something. So it's it doesn't even consider the one in the neighborhood of galaxy, for example. And in our case, we will just perform a blind search, and still with this blind search, we can compare if we find then the number of objects that we find, and we can finally confirm as a MIlli-Lenses, or if we don't find, we can still compare with this prediction in this case, but also for example, for also different dark matter model, because they also predict a different number of, so it requires also a very detailed calculation for the different scenario, but.
Okay, thank you very much. Thanks a lot.
Okay, so you have another question for Carolina? Okay, if not, let's thank Carolina. Ah, yes, we have one. So Nikos Mandarakas is asking how many confirmed lenses would comply with a lambdaCDM model?
How many? So how many? If I understand correctly, so how many dark matter halos in this range of masses of interest we expect from the lambdaCDM prediction?
Well, the question is how many confirmed lenses would comply with a lambdaCDM model. So I suspect from the sample that you have, with how many lenses you would be happy in order to accept the lambdaCDM model.
Yeah, so
that's
then
my interpretation of his question. Okay.
Okay, then I think is related to the number predicted by the lambdaCDM. So the lambdaCDM in this, if we integrate, I think can you see my slide still, or?
Yeah, we can see the plot.
Okay, perfect, exactly. So if we integrate the number, so in this, given by this, this prediction between the range of mass of interest for this project, that is 10 to the 6 and 10 to the 9 solar masses, we got roughly 2 in 10 to the minus 3. Yes, that is roughly here. That is the mass density that we expect for the case of dark matter sub-halos free floating in the flow. In the field, sorry. So it's anything basically below still will kind of question this prediction.
Okay, and do you have a feeling how many lenses would this produce out of your sample?
No, I didn't think about that yet.
Okay, because I feel that this is the question, but never mind. Yeah, okay.